Hi class, so we're doing 18.3, this is part 2, and we're looking at example 10, and it says, given that the measure of angle A is 90 degrees and the measure of angle ADB is 40 degrees, and BD is parallel to CE, triangle ABD is similar to triangle ACE by angle-angle similarity, and we have these two examples, 8, 10, and 11. So we're going to figure out a few things, and then we're going to look at a table of values and ratios concerning the two. Oh, I guess I kind of need to see that. Okay, so for example 10, the measure of angle E is going to be what? Well, we know A is 90, so it's a 90-degree angle, and ADB is 40, so this angle right here is 40 degrees. Okay, so if that's 40 degrees, then angle A also has to be 40 degrees because it states that these two sides are parallel. And if those two sides are parallel, corresponding angles will be congruent, so angle E must be 40 degrees. And then let's look at AE. So that's A to E, that's this side right here. And that's going to be 5 plus 3. I have to add those together, and we're going to get 8. Okay. And then AC is AC, this side right here. It's going to be 2.52 plus 4.2, which is 6.72. All right, and this is 8 that we figured out. Okay. And then next, the measure of angle E again is going to be 40 degrees because D was 40 degrees and these sides were parallel. And then AE, so that's this bottom, is going to be 4.76 plus 3.57. And that is 8.33. So 8.33. And then the other side is 3 plus 4, which is 7. All right. So those are our measurements. Now, I'm going to have to take those off the screen, so hopefully you've gotten them written down. You can use them as we go about figuring out what these table values are. Now, I would suggest you just go ahead and doing them. I don't want to spend a whole ton of time on going back and forth and back and forth, so I have them already pre-written out, but you can be checking as we go, check your own paper like I'm going to, because it doesn't all fit on the same screen, which is unfortunate, but we'll make do by I'll check mine over on the side. And AB, now notice these are, there's a little line here, example 10, and example 11, and example 10, and example 11. So we're looking at the two different examples that you see above. So as you check your paper and look at example 10, AB is along the vertical side, and it's 4.2, and then BD is the hypotenuse, and it's 6.53, right? And then AD, I'm just going to find them all, and then I'll put them in the calculator in a second. AD is along the bottom, horizontal, it's 5, and BD is, again, hypotenuse, and it's 6.53 again. All right, and then AB is vertical, 4.2, divided by AD, which is 5. All right, now that I've got those all written out, I'm going to go ahead and put those into the calculator. So 4.2 divided 6.53 is 0.64. It says round to the nearest hundredth. So that's the second spot after the decimal. And then 5 divided by 6.53 is 0.77. And 4.2 divided by 5 is 0.84, rounded. Okay. Now let's look at example 11. AB is along the top, along the vertical side there, and it's 4. And then BD is 6.22. And then AD is 4.76. And BD, that's the hypotenuse again, BD is 6.22, or the smaller of the two similar triangles. Note that they are similar triangles. So we're just taking side ratios. And then AB is 4, and AD is on the bottom, the horizontal, 4.76. Okay. Now, notice that these AB and BD, AB over BD is the same. sides that we're looking at their ratios. So we're looking at AB over BD in both example 11 and 10, and so on and so forth. AD divided by BD, we're finding that ratio. It's the same sides that we're comparing or finding the ratio for in both of the two similar triangles who have different measurements. And then AB over AD, again, are sides that are the same sides, but we're comparing the ratio of two sides for two different sized triangles, even though the angles are the same. And when you take 4 divide 6.22 and round to the nearest hundredth, again, you get 0.64. When you take 4.76 divided by 6.22, and round, you get 0.77. And when you take 4 divided by 4.76 and round, you get 0.84. So when you're looking up here at the triangles, you notice that they are different sized. This size is 6.72. This size is 7. That's the one side of the larger of the two triangles. Though the angles are going to be the same, they are similar by angle similarity. Their side measures are a little bit different. Here AB is 4, here AB is 4.2, AD is 4.76 for example 11, whereas example 10, AD is 5. So we have two similar triangles, two sets of similar triangles with the exact same angles, though they're both similar triangles with different sizes. And they're not far off, a little bit different. But did you notice that in the first row, you have 0.64 as a ratio of sides for example 10, and you have 0.64 as a ratio of sides for example 11. So you're taking AB, this side, in both cases, and you're dividing by BD, this side, in both cases. So no matter the size of the triangle, when you take the leg divided by the hypotenuse, or the opposite, the 40-degree angle, opposite divided by the hypotenuse, in both cases, opposite divided by hypotenuse, all of a sudden you get the same exact ratio, 0.64. That happens no matter how big or how small or how different size that triangle is, as long as it's opposite and the hypotenuse of a 40-degree angle in a right triangle, you're going to get the same ratio every time. Same thing goes for AD divided by BD. So you're looking at AD, this bottom part here, and dividing it by the hypotenuse. So adjacent to the hypotenuse, once again, adjacent to the hypotenuse is not the same as opposite to the hypotenuse, but in both cases, no matter how small the triangle is, when you take AD divided by BD in both examples 11 and 10, you get 0.77, that A over H. And then the last one is AB, which is the side divided by AD, which is the other side. So you have one leg, AB, which is a smaller leg or opposite the angle, and then the adjacent to the angle is 5. When you divide that, you get 0.84. And if you do it for the other triangle, opposite divided by adjacent, in example 11, you get, again, same thing, 0.84. So the truth is, no matter how big or how small those triangles are, when you have a 40-degree angle in a right triangle, if you take opposite divided by hypotenuse for the 40-degree angle, you get 0.64. In both cases, if I take adjacent divided by hypotenuse in both cases, I get 0.77. If I get opposite divided by adjacent in both cases, I get 0.84 for that 40-degree angle. Happens every time. So what's happened is, in your calculator, you've programmed what is the opposite divided by the hypotenuse for a 40-degree angle. Okay? And that happens to be sine. If I do sine 40, guess what I get? I don't know if you can see that, but it's 0.64. So that's a ratio of the opposite to the hypotenuse sides of a triangle for any 40-degree angle in a triangle, no matter what. We're going to try it for the larger of the triangles. Those were the smaller. We're referencing smaller ones. Now let's go ahead and do the same measurements for the larger one. So AC is 6.72, CE is 10.44, AE is 8, CE is 10.44, and again, I'm just looking over to the side because that's where my triangles are, and I don't want to move the toggle back up and down. And then AC is 6.72, and AE is 8. Okay, I'm going to go ahead and do example 11 now, and then I'll plug them into the calculator. 7 over 10.88 AE, and that's the larger side, horizontal side on the example 11. So AE is 8.33 and 10.88, and we'll see what that's approximately. And then AC is 7 and AE is 8.33. All right, so again, these are the same ratios. These are opposite to hypotenuse. These are all adjacent to hypotenuse, and these are all opposite to adjacent. So 6.72 divide 10.44, guess what? 0.64. And then guess what? 0.77 and 0.84, 0.64, 0.77, and 0.84. So there are 4 different sized triangles with a 90, 40, and I guess the other angle would be 50, 90, 40, 50 triangle. The opposite to the hypotenuse, no matter how big or how small, I'm just going to highlight right here, is 0.64 when I take opposite to adjacent. Okay? If I take adjacent to opposite on all 4 different triangles that are similar triangles that have the same 40-degree angle, I get 0.77. And if I take the opposite and divide the adjacent on all 4 different size triangles, I get 0.84. Happens every time. Now, I already showed you what sine 40 is if I plug that in the calculator, and you can do that yourself on your calculator. Just hit sine and then the angle. The angle always follows the trig function, sine. And sine 40 is 0.64. And guess what happens if I hit cosine then 40? I get 0.77, which is adjacent over hypotenuse, and sine is opposite over hypotenuse. And tangent 40, if I hit tangent, remember we did opposite to adjacent there, opposite over adjacent, that was 0.77. Isn't that crazy? No matter how large or how small the triangles are, you're going to get the same ratio because you're taking a side and dividing by a side, and that's going to be a ratio every time, and it will always simplify to the same exact decimal every time for those similar triangles. All right, so that's the end of the lesson. You can get going on the homework. Go through, you have to label sides. That should be pretty easy. Remember to go from the angle that you're referencing. And then the next part are the triangles in the pair similar? If so, state why. So you're going to be checking for similarity, and then you're going to be filling out your own table like we did in our example. All right, that's 8-3. Good luck with that.